Today we're going to go over how to find the second derivative of a function using implicit differentiation. So the first thing you need to do is find the first derivative using implicit differentiation. Find dy dx. Once you do that, you're going to start finding the second derivative, which is going to require the use of the quotient rule for almost every problem. Once you have this, you'll see you have dy dx in your second derivative, so we're going to replace it so that we have only x's and y's and no longer have a dy dx. After I do that substitution, we're going to have to go through some algebraic steps to simplify completely. It may require an additional substitution, which you'll see in the couple of examples I'm going to show you. So our first example, x squared plus y squared is equal to 25. So the first thing we need to do is find the first derivative. So I start with the derivative of x squared being 2x. Then the derivative of y squared is 2y dy dx. And then that's equal to the derivative of 25, which is 0. Now we need to rearrange this so it says dy dx equals. So we are going to subtract 2x from both sides to get 2y dy dx is equal to negative 2x. And then we're going to go through and divide by 2y. And we're going to end up with our first derivative, dy dx, is equal to negative 2x over negative 2y. The 2's can cancel off to give us just negative x over y. So we're going to use that derivative to find the second derivative. So here we go. We have dy dx equals negative x over y. Now that's technically a function over a function, so I need to use the quotient rule to find the second derivative. So d squared y dx squared is equal to, here we go, quotient rule, low d high, negative 1, minus high, negative x, d low, derivative of y is just dy dx, all over low squared. If I get rid of all of the parentheses up top, I'm going to have negative y plus x dy dx all over y squared. Now the problem is I have too many things going on here. I want to get rid of this dy dx and replace it with something that just has x's and y's in it. So that dy dx is equal to the negative x over y that we found at the beginning. So we're going to substitute it in. So our derivative is now going to become negative y plus x times negative x over y all over y squared. And now I have a fraction in a fraction. So the easiest way to clear that out is to multiply by the denominator in the top. So I'm going to multiply the top by y and the bottom by y to make that go away. So here's what I'm going to get from that multiplication. Negative y times y is negative y squared. I'm going to have plus x times negative x, and those two y's cancel off, so I'll be left with minus x squared all over y squared. Oh, I'm sorry, y cubed. So negative y squared minus x squared all over y cubed. Now I have a derivative that has just x's and y's in it. However, if I look back at the original function, there might be something more that I can do. So our original function was x squared plus y squared is equal to 25. Look at the derivative that we came up with. If I focus on the numerator, I have negative y squared minus x squared. Well, if I factor out the negative, that gives me y squared plus x squared. Don't forget about the y cubed on the bottom. And now what I see is I have x squared plus y squared here. Well, that's what my original function was. So I can replace it with a 25. My final answer for the second derivative of this function will be negative 25 over y cubed. And that's how you find the second derivative of a function using implicit differentiation.